Okay, so I think you guys are seeing my screen here. Yep. Okay, so we've gone through the first page of the review. You can see the first page was covering just quite basic questions about vectors and projections, and then planes, all fundamental stuff. And then we started working on the next chapter, which is vector valued functions. We've covered all that. Only did a few questions. Please do not assume that I can't ask anything at all on vector valued functions. So there was more to it than just curvature and the two accelerations in the decomposition of the acceleration vector. So, I mean, these are the most important things, but don't forget there's a unit tangent and the unit normal and the unit binormal. So you might want to add these formulas to a formula sheet if you're making one. I've got the formula on here for curvature. I would just scan through all that and see what you see. For projectile motion on the next page, I think we said R of t. Now I'm just going from memory here. The x component is a script v naught cos theta times t plus any initial x naught position. And then the y component is a negative 1/2 g t square plus script v naught sine theta times t plus the initial height, so that would be y naught. Okay, so that's our formula. I think we did have a formula for the range. So if x naught, y naught, the initial position is the origin 0, 0, then the range, now that's a bit of a challenge here. I think it was like v naught squared sine 2 theta over g, but I gotta look, so hang on. Maybe somebody here knows. It was in section, hang on. If you know it, feel free to share. I'm looking it up. I think it was in 13.4. Yeah. So the range is v naught square sine 2 theta over g. That sounds familiar. So script v naught square sine of 2 theta, which is the angle of inclination for the projectile, over gravity. Okay, so I don't see, you can find the maximum height by taking derivatives and stuff like that, but I think this is good enough. Setting the derivative equal to 0 on the y coordinate will get you there, or at least part of the way there. Okay, any questions? Okay, so I don't know. You guys have studied projectile motion so many times that it's kind of a low priority. Anyway, so the next thing is on differentials. So you've got a function here, the error in z using differentials. So just remember dz is approximately the error in z. So this is approximately delta z, which is the error. dz is the change in z on a linear approximation, which is tangent plane. So the formula is just fx dx plus fy dy. That should be pretty familiar. That's the total differential. Okay, so maybe we could do fx down here. Oh, I made a couple of mistakes there. So let me fix that. X is -5, y is 2. So that should be times 2. I hope that's right. And nope, that's a -5. Okay, third time's the charm. And then x to the third minus a, so that'll be -5 third minus 8. Half a moment here. Okay, so nuts. Just one sec. Okay, so first one should be 198, I hope. And the second one should be -133. Okay, so fx is going to be the 198. dx is the maximum error in x, so you'll do 0.3 plus fy, which is the -133, times dy, which is 0.1. Okay, and so this comes out to be 46.1. So it's in decimal. I don't mind giving an answer in decimal. Okay, that's the absolute, that's an estimated absolute error. If it asks for the relative error, then you'd have to divide by z. And so I'll just put that in parentheses. So that the relative error is dz, which we just computed over z. Okay, I probably should say it is approximately this since it's a tangent plane approximation. And it doesn't ask for it, so I'm going to move on. Does anybody have any questions about this one? Yeah, Nero. Monday's the last day, Nero. So I just saw your comment. Okay, I don't see or hear any questions about that one. So let's go to B. Okay, so just remember, if you're going to do a directional derivative, the unit vector, well, the direction vector has to be a unit vector. So you're going to do the vector 1, 2, and make it a unit. So you have to divide by the square root of whatever. This will be 1 square plus 2 square. So you could say it's 1, 2 over the square root of 5. That would be fine. Okay, any questions? We've done most of the work for the gradient. So the gradient of f is fx comma fy. So we have to evaluate this at 3, 1. So if I put in a 3 and a 1, fx gets a 3 times 1 square. Wait, sorry, 3 times 3 square times 1, comma, nope, plus 24 times 3, because x is 3, comma, and then x to the third minus 8. So that'll be 3 to the third minus 8. Okay, which comes out to be 99/19. Okay, so I'm just taking the gradients from above. Okay, so the directional derivative in the u direction of f at the point 3, 1 is going to be the gradient of f at 3, 1, at 3, 1 dotted with u. That has to be a unit. So here we're just doing this vector 99, 19, and dotting it with the 1, 2 over the square root of 5. So that's pretty straightforward. So I got 137 over the square root of 5, which is 137 root 5 over 5. Okay, so just have a moment if you'd like to ask a question on this. Is there anything at all? Now C, it's using the same point here, 3, 1, as the point in the directional derivative. So here you need fx at 3, 1, but we did that up above. It's 99. And fy at 3, 1 is also up above. It's 19. So I'm just pointing the 99 to, oops, the 99 is this guy, and the 19 is that guy. Okay, so the tangent plane is as follows. Plus the z naught. So z naught is f of x naught y naught. Okay, so this is for z equals f of x, y. Okay, so here we can say z is fx, which turned out to be 99, times x minus x naught, which was 3, plus fy, that was 19, times y minus y naught, that'll be y minus 1, plus the z naught, which I don't know if I computed that ever. So f of x naught, that not y naught, this will be f of 3, 1, which I have done already. It's 127. So I'll just kind of box that in. So you add the 127 to this. Now I did simplify this a little. I'm gonna make a little room for the simplified version here. Okay, so when you simplify this, it's z equals 99x plus 19y, and I think it's minus 189. Can that be? Yeah, minus 189. Okay. I'll take a second and wait for questions on this. Any questions? Okay. Well, then it's asking for relative extrema or saddle points. So we need to set, to find critical points, we set fx equal to 0 and fy equal to 0. I've already computed those, so let's grab them. And then always try to factor these if you can. So clearly I could factor out at least a 3x on this first. And so you'd have an xy squared minus 8, right? Or plus 8, I guess. And of course, that has to be 0. X to the third minus 8 can be 0 as well. Okay, and I guess we could factor that, but it's not nice. It's going to be x minus 2. Hang on. That's a difference of cubes. So you're going to have x squared plus 2x plus 4 is how that factors out. Equal to 0. Any questions? Looks like x has to be 2. And that's the only possibility because here, here you get x equals 2. Here, x is imaginary. There's 2 imaginary solutions from the second one. And we're not interested in those. Oops. Okay, any questions? You can set that equal to 0 and you'll have to use quadratic formula and it'll be imaginary. Okay, so x equals 2. And then we can set 3x times xy squared plus 8 equal to 0. And we should note that x can't be 0, even though this guy says it could be 0. X has to be 2 because of the second equation. It can't be 0. So I'm going to just note here x is not 0. And then here we can say 2y squared plus 8 is 0. I think there's a mistake somewhere. Hang on a second. Okay, so the mistake, I don't know if you guys see it, but this is not supposed to be a square here. Can you guys see that? It was not squared here. So I picked up a square there somehow. So let's fix that. I think that's the way it should be, xy plus 8. Okay, so let's erase it down here, xy plus 8. And then this would be just 2y plus 8. And so out of that, I think y comes out to be negative 4. Okay, so our solution, the only critical point is 2, negative 4. Okay, any questions about that? Let's take these second partials now. So we're going to have an fxx. So it's like 6xy plus 24. Maybe an fxy. So there, you're going to get 3x squared. And then fyy. So that's just 0, I think. Now, we could evaluate at our point. So if we do fxx at 2, -4, what's that? So that's 12, -48 plus 24. I think that's -24. And fxy at 2, -4 is just going to be 3 times 4, so that's 12. And of course, fyy will be 0 everywhere. Oops, sorry, did not mean to do that. Don't know what happened there. So at 2, -4, as I say, is 0 everywhere. So then there's this d, which is fxx fyy minus fxy squared. So d at the point 2, -4. So you're going to get -24 times 0 minus 12 squared. So I think that's -144. Oops. Okay, and just as a review, oops. If d is positive and fxx is negative, that's a local max. Okay, if d is positive and fxx is positive, that's a local min. And finally, if d is negative, that's a saddle. And so from that, we see because d is negative at this point 2, -4, so f has a saddle.
Professor?
Yeah.
I think the 12 doesn't have the square.
Wait, say that. I didn't understand.
Yeah, the d 2 to -4 and then -24 times 0 minus 12. The 12 doesn't have square, I think.
So are you talking about this right here that I've just circled? I don't see any other 12s that are being squared.
That's a formula. Okay, got it.
Yeah. It's got this thing right here.
Because I'm thinking above the x y equal 3x squared. So.
Yeah. No, I totally understand. Oh, but x is 2, right? So I think everything's okay here. So anyway, f has a saddle at 2, -4, and I guess we're done. Okay, any questions? So this looks pretty serious here. Okay, so on number 7, they say show it's conservative. So I want you to use the curl to do this. So let's just say using the curl of f. Okay. So let's go ahead and do the curl of f. Well, and of course, the formula is del cross f. So we'll put in the components here. Okay. So then for the I hat component, we're crossing this way. Okay, and I think that looks like 0 to me because the partial with respect to y of this function of z is going to be 0. And the partial with respect to z of this function of x and y is going to be 0. So here we're just going to get 0 minus 0. Any questions there? Okay, now for the j hat component, remember we do a minus sign and then parentheses like that. J hat always gets negative. Okay, and so here we're going to do this way. And I think we get the same thing. With respect to x, a function of z is 0. With respect to z, a function of y is 0. So once again, we're going to have a 0 minus 0. Like that. And then for the k component, we go, oops, we go like this. So with respect to x, of x e to the y, I think that'll just be e to the y minus. So again, we did that. Now this way, the derivative with respect to y of e to the y, that's again e to the y. So you get an e to the y minus e to the y. And of course, this is just a 0 vector. Since curl f is 0, f is conservative. Okay, any questions there? Okay. Now, let me see. Part C, part A. Okay, weighing. You guys hold on just a sec. Yeah, I'll try and do that. Lena, I see your question. I'll try to do that. Weighing. Real quick here. You wanted to see A, right? Hey, will you let me know when you've got this? Just let me know when you're done.
I'm good, thank you.
Thank you. Okay. Now, the fundamental theorem of line integrals requires a potential function. So we need to find the potential for big F. Which is related to potential energy, right? Little f of XYZ such that the gradient of little f is big F. We know that it exists because it's conservative. All conservative fields have potential functions. So gradient of little f is just three partial derivatives, fx, fy, fz. Okay, this has to be big F, which I will just copy down here. It's e to the y, xe to the y, z plus 1 e to the z. Like that. So that's big F. Now, pairing things up, F would be the antiderivative of e to the y dx. So this is going to be x. Remember, this is x. This is a dx integral with an e to the y, so that's just constant. The antiderivative is x times the constant, so that's x e to the y. But then any function of y and z will be treated as a constant as well. So you'd like have a c1 of y and z, like that. But f is also the antiderivative of x e to the y dy. And that's super easy. That's just going to be x e to the y plus another constant. This is dy, so a function of x and z would be treated as a constant. And these obviously pair up pretty nicely. If you think through the logic, C1 and C2 have to be the same. C1 doesn't have an X, so C2 cannot have an X. So this C1 and C2 have to really just be functions of Z. C2 doesn't have a Y, so C1 can't have a Y. That's kind of the logic there. It doesn't matter if that makes sense. We have a real simple way to do it. You just list all the functions you get, the real functions. Anyway, the third component, oops. So the third component is the antiderivative of z plus 1 e to the z dz, which is going to be, I'm going to line it up this way. I'm going to put a z e to the z. You can check the derivative of that is z plus 1 e to the z. Okay. But you're also going to have a third constant function, C3. This would be a function of x and y. Okay, I put that first because that will compare to these two guys here. And this compares this way. So in the end, you just list all the functions you see and don't list anything twice. So f of xyz, oops. F of x, y, z, my potential function, is going to be x e to the y plus z e to the z and then plus just an arbitrary constant of integration. Okay, this is your chance to ask questions. Anybody? Okay, so then they're asking that we compute the work along a path. So work along curve C is a line integral. This is not a closed path. Okay, and we just do the field dotted with the displacement differential like this. And the fundamental theorem of line integrals says you can just do this as f of r at b. Now b is the endpoint, so I guess I'll just put a 1 here, r of 1. This is the endpoint. Minus f at r of 0. I think t is going from 0 to 1, right? Yeah. So r of 0, that's the start point. Okay. Now, we can choose any value for c here. So let's go ahead and just say, let's choose c equals 0. Because it subtracts out anyway. The c always cancels when you subtract these two. I showed that last time. Okay, so r of 1, let's just write it this way. This would be f at r of 1. So r is way up here. At 1, that's 1, 1, 1. So 1, 1, 1. Minus f at r of 0. I think that's going to be 0, 0, 0. Like that. Now, all we're doing is showing that work is just change in potential energy. So we're subtracting the two potential energies rather than doing a line integral, which is a lot harder. So f of 1, 1, 1 looks like it's going to be E plus E. So that's 2E. And 0, 0, 0 looks like you're going to get 0. So this is just 2E. And I'm checking my work here, make sure there's no mistakes. Yeah. So it's your big chance to ask questions about this one.
So I just want to clarify that F111 minus F000, that is inputted into the potential function, correct?
Yeah, they are. So the potential is this guy where C is 0. Just ignore the C. It cancels out anyway. So this is your F, but the 111 comes from R. Again, this is your endpoint. So you're doing R at time 1. That's your final position on this curve.
And then
So if you look at R of 1, you're just doing 1, 1, 1 here. And then the start point is where T is 0. So that's going to give a 0, 0, 0 there.
okay,
Make sense?
thank you.
No problem. And thanks for asking. Does anybody else want to do a question on this? This is a new topic. It's not review. This was part of whatever the last chapter is. Is it chapter? I don't even know. Chapter 16? Whatever we just finished. Okay. Any questions there?
We can choose C to be 0 always to do that, or like.
You can pick anything you want for C and it'll cancel out anyway, because this one ends up with a plus C and this one ends up with a plus C and they subtract out.
Okay.
It's the same thing as when you do, you know how when you do an antiderivative and you used to always put a plus C there, right? But when you do a definite integral, you don't do the plus C, do you? because they cancel.
Okay.
This is just a generalization of a definite integral, but you're integrating on a curve rather than the x-axis.
Thank you.
Okay, I hope that makes sense. So the plus c's are irrelevant because they vanish, just like they do with a definite integral. Okay, let's go on. This one, it says to evaluate the line integral directly. So we're doing another problem where it's work. Okay, just work. But this time we can't use the fundamental theorem of line integrals. So this one means there is no potential function. Okay, so you're just gonna have to do this the hard way. Okay, so we've got our field. What we need is dr. So when we refer to x, this is x, it's cos t, and y, sorry, 2 cos t, and y will be 2 sine t. Dr is defined as r prime of t dt. So r prime will be negative 2 sine t, then 2 cos t, dt. Now my field is going to be, as you can see, negative y to the third, comma, x to the third. Okay, but if we evaluate it where y is 2 sine t, we really mean negative 8 sine cubed t, and x is 2 cos t, so that'll be 8 cos cubed t, like that, dt. No, that's just f. There's no dt there. No differential, my bad. So I get that right? Y to the third's got the sine, x to the third's got the cosine. Okay. And so when we do the integral along our curve C, of f dot dr, what that really means is the integral where t goes from, as instructed, 0 to 2 pi. And then we're going to dot f, which is this 8 sine cubed, let's say cosine cubed. Okay, and that dots with dr. Like that. I don't like the looks of it. Gosh, this is horrible. Here we go. So we're going to have a 16 sine to the fourth t. Oops. Plus 16 cos to the fourth t dt. And so sine to the fourth, remember sine squared t is 1 minus cos 2t over 2. And sine and cos squared t is 1 plus cos of 2t over 2.
Professor?
Yeah.
Could we do a shortcut and then just pull out the 16 and then pull out a sine squared plus a cosine squared to make that 1? So it'd be 16 times 1 times 1? Or am I missing something?
I think you are.
Oh, wait, never mind. I see my mistake.
Yeah, the fourth, this is sum of fourth powers, and there's no way to factor that. You can't recover the squares.
Yeah, absolutely.
It's an absolute tragedy. I wish we could. So here, Unfortunately, what we're going to have to do is the brutal work. I mean, clearly we can put a 16 out, but you're still going to have the sine to the fourth, so, and cosine to the fourth. So what we're going to do is write the sine to the fourth, which is going to be sine square square. So inside we're going to put 1 minus cos 2t. This will be over 2, and it's squared. And plus, same thing for the cosine squared squared. So this would be 1 plus cos 2t over 2. This is also squared. Isn't that beautiful? Now the 2's are going to get squared in the denominator. That's a 4 on both denominators, which I'll bring out as a 1/4. So I think I'll write this as 16 with a 1/4 out with it. Okay, and then we got the 0 to 2 pi. And then unfortunately, I think I have to square this out. And so you're going to get the following. You're going to get a cos squared 2t. You get minus 2 cos 2t. You get a plus 1. That's the first part. And then the second part, you're going to get a cos squared 2t. You're going to get a plus 2 cos 2t. And then plus 1. And of course, there's a dt out there somewhere. Like this. And of course, some cancellations, fortunately, not much. The negative 2 cos 2t cancels the positive 2 cos 2t. The ones will combine. I think you 2 cosine squared 2t, right? So I think we see a 4 integral 0 to 2 pi. It's 2 cos square 2t plus 2, right? Like that. And unfortunately, cos squared 2t is going to have to get reduced as well. So here you're going to get a 4 and the integral from 0 to 2 pi. So here you're going to have, I guess I'll leave the 2 in for a sec. So you're going to get a 2, and then this is going to be 1 minus, no, plus cos of 4t, right? And that's over 2. And then plus that other 2. So there's a dt. 2's cancel. Oops, that is an accident. So my 2's cancel. And I end up with a cos 4t plus 3, I think. So I think this comes out to be the 4 integral 0 to 2 pi. I think we have a cos of 4t plus 3 dt. And of course, the trig part's going to zero out. So anyway, you get 4, and then in front here, the antiderivative of cosine is sine, right? So you're going to have a 1/4 sine 4t plus 3t. And that's going to go from 0 to 2 pi. You guys all fitting this into the space provided? Okay. So then in the end, we've got the 4 times 0, I think. Sine of, any multiple of pi is going to be 0. And plus 3 times 2 pi is 6 pi. So I think we're going to get 24 pi out of that. All right, any questions there? Isn't that lovely? That's a line integral.
Professor,
Yeah.
for the 2 cosine squared 2t plus 2,
Mhm.
can we factor out the 2?
I would have, but you know why I didn't? I knew that I'd end up with a 2 down here. Can you see what I'm circling?
Yeah.
So if you factor it out, you're going to end up with a fraction inside, and that's why I didn't do that. Certainly, you could do that,
Okay.
but you'll have a 1/2 inside.
Mhm.
So however you want to handle it, either way, you should get the same answer. Okay, any questions there? Okay, so that was fun. On number 9, they want us to use Green's theorem to convert the line integral to a double integral and integrate in polar coordinates. Okay, so you ready? So first of all, we could draw this thing. R of t is 2 cos t, 2 sine t here. That's just a circle. T is 0 to 2 pi. So let's go ahead and draw this. Okay, so this is my R of t. This I'll just call it curve C. Okay, it's a counterclockwise orientation in Green's theorem. The region inside is R. Okay, maybe I'm going to do a quick shading job here. A shady job. Okay. So, what we know is Green's theorem. Let's see if I can remember it. So we have a line integral, and this was a closed loop. So I'm going to put a loop around this thing just to indicate that it was a closed loop on our line integral, counterclockwise orientation. Okay, so Green's theorem says that this thing, closed loop of, I'll go ahead and write f dot dr here for work. F dot dr, the field, the vector f has the components p comma q, like that. Dr can be thought of as a dx differential comma dy differential. That's another way of doing it. Okay, so you can rewrite this with a dot product like this. So it's p dx plus q dy. These are all going to give the same result. They're all the same thing, just different ways of writing it. Okay, but Green's theorem says that you can rewrite this as a double integral over the region inside R. Now this is the part where I get a little confused. It's the curl. So the curl, I think, is q y minus p x, and then no, it's the other way around. It's qx minus py. I'm sorry, you guys. It's qx minus py dA, like that. So that's Green's right there. Any questions here?
I don't have a question about this, but I had a question about what parts of chapter 16 are going to be on the final.
Well, that just chapter 16 is the only thing I haven't tested. So I think you should assume that anything in chapter 16 could be on the final. I'm not going to limit that because that's, again, see, it's the one thing I need to cover on this final. Everything else has been tested.
So
Okay,
you think there will be more of chapter 16 on it, like more than
Yes.
one question?
Yeah, I would say 2/3 of the final will be chapter. This is a guess, okay? But if I was to guess, I'd say about 2/3 of the final will be chapter 16. And you'll see that most of the pretty much the rest of this is all chapter 16. So I only did basically 2 pages. Well, I don't know. I got 2 pages of old review stuff, and I'm not promising to hit all of that. Okay.
Okay.
It's the new stuff that's critical. Okay, so keep on going. So Q, you have to go back to our field, the original field. This is our P, and here's our Q. Okay, so if you do QX minus PY, maybe I'll identify up here. P was, oh gosh, negative Y to the third. And Q was X to the third. Okay, so so here we'll say double integral over R. Okay, so it's QX minus PY. So that's going to be 3x squared minus negative 3y squared dA. Oh, that's nice. I don't mind one bit doing that in polar coordinates, right? Because x squared, this would be, this is going to be double integral. We'll take the 3 out. And double integral in parentheses x squared plus y squared dA over R. So here now we're switching to polar coordinates. So this will be R squared. dA will be R dr d theta. Okay. R would go from, what's the radius of the circle? This is circle of radius 2. So let's put some 2's down. Okay. So it's a circle of radius 2. R would have to go from 0 to 2 and theta from 0 to 2 pi. Any questions? That doesn't look too bad. So we get the 3 integral 0 to 2 pi, integral 0 to 2, and we've got an r to the third dr d theta. So we're going to have a 3 integral 0 to 2 pi. And here you're going to get a 1/4 r to the 4th, right? Where r goes from 0 to 2. Okay, so I'll just group that. And then there will be a d theta. So I'll just break these down. You got a 3 times the r to the 4th. That's going to be 1/4 times 16.
Professor, I don't know if maybe it's just me, but it's taking a while for the work to be uploaded onto the.
Oh, really?
Yeah, so we can't see past the double integral of x squared plus y squared dA.
How about that? Okay, so let me stop the share. You guys are all seeing that?
I see it from.
Sorry, I didn't know if it was just me, so I don't want to stop everything.
Yeah, no, it's good. I'm glad you said it. Thank you for saying that. All right, so let's try again. Now, I assume you guys can see that.
Yes, thank you.
That's good. Okay. Now, what if I move it around? Does it move with you? Is it going up and down?
Yes.
Yeah.
Yeah, I think the internet gets a little bogged down sometimes. Anyway, so this the 1/4, 3 times 1/4 times 2 to the 4th. That's 16. And then the integral from 0 to 2 pi on d theta would just be 2 pi. So I hope that this is going to be 3 times 4, which is 12 times 2 is 24 pi. And this should be exactly the same answer as what we got before. They are the same problem, but just done with different tools. Okay, any questions about that? Completely different, right? But Green's theorem says they're the same, and they are. Any questions? So I have problems like this on the final where you're going to basically evaluate things 2 different ways because all of the theorems basically give 2 sides of an equation that should give the same result. Okay, so in this one you have a single integral that gives the same result as the double integral. That's Green's theorem. But the divergence theorem has a similar kind of a thing going on, and Stokes' theorem has a similar thing going on. So we better keep moving here. Okay, this one's asking, didn't give much space, did I? Okay, so I have to do the flux generated by that field through a sphere of radius A. Okay, now we are constrained to the surface, remember, because it's a surface integral. Okay, you cannot leave the surface. Okay, and if you are constrained to the surface, keep in mind it's a sphere of radius A. So the square root of x squared plus y squared plus z squared had better be the radius of the sphere. Any questions about that? Also, on a sphere, what we have is that ds, and I don't know if I should rub this in your face or not. What did we do? Is this in 16.7? So I'm flipping through 16.7 real quick here. Okay, so it's not 16.7. Let's look. I'm peeking back to see if I can find this. Could be 16.8. Oh, golly. Did not mean to show you all my family wedding pictures here. Hang on. Now, where am I? Is this 16.8? Yeah. All right, so it's not there. So it's got to be 16.6. Here we go. This is it right here. Formula sheet for your final. For a spherical shell, rho equals A. Here's all the info. I recommend you not forget to put this on your formula sheet. Because to derive it, it took me a page and a half or 2 pages of work. I don't think you want to derive this on the final, okay? So let me paste it over into the review. I'm going to make it small because it takes up a lot of space. Okay, so there's this. So when we do flux, it's a double integral. This one's a closed surface. So I'm going to put a little circle around to indicate it's a closed surface with an outward normal. Closed surfaces have outward normals. Okay, I'll put a little s down here to indicate the sphere. Okay. We do flux is F dotted with the surface area differential, which is a vector that is normal to the surface at every point. Okay, and what I did was, another thing I could add to this is just remember that R is the position vector. So R is just X, Y, Z here. And so when I look at my field up above here, I could just say that my field is a position vector, R, over the radius of the sphere, A. Okay. Now you can do all this trig work and all, or you can try and think a little bit above the problem. See, what you've got here is a double integral of the field, which is the position vector divided by the radius of the sphere. Okay, and if you think about it, that's a unit vector right there. And then you're dotting this with a ds, and ds, the vector, is this one down here. Okay, so you can say this is dotted with the scalar a times the radius sine phi d phi d theta okay, and the a's cancel, and it's still over the surface. You know what, I'm not gonna, I'll go ahead and leave the s down there for a bit. Okay, so the first thing to notice is that a cancels, and you end up with a r dot r, which is the magnitude of r squared. So this is a double integral, oops. So this is a double integral of the magnitude of r dot r. Sorry, of r dot r, which is the magnitude of r squared. Okay, so this is sine phi d phi d theta. Okay, and I'm going to still leave an S on here to indicate I'm still thinking of this as a surface integral. And what's the magnitude of R? If you're constrained to the surface? Of the sphere, the magnitude of your position vector should be the radius of the sphere. Okay, you can work that out if you want, but it's just A, the radius of the sphere. So you can say, ooh, that right there, magnitude of r squared is just going to be a squared. Okay, so now look at this, my double integral. I'm going to go ahead and make it look like a surface integral again with the s down here, and recognize that, well, hang on. I'll do that in a sec. So what I really have here is an a square sine phi d phi d theta. Okay. And then recognize next that that is ds the scalar. Okay, not a vector. Now I'm just doing a surface area, because this thing here is just ds the scalar differential for surface area. So this would be a double integral. Again, it's a closed surface, so I'm going to go ahead and give it its circle here. I'm making it look like a surface integral again, because now the differential is a ds differential, but it's just ds. There's nothing left. Now, what would that be if you just add up bits of surface area? This would be the area of the surface. Okay, that's just a definition. That's probably the simplest surface area formula you'll see. So the area of our surface, again, this is a sphere of radius a. So the formula for the area, the surface area of a sphere is 4 pi a squared. So you don't actually have to evaluate that integral if you're really paying attention. And there are several problems on the exam that come down to an object that you know the formula to compute its volume or its area. And if it turns out the integral is just giving the area or the volume of a commonly known object, I would not evaluate the integral. I would just give the formula for the area or the volume. Okay, like I did here. Is there any questions? I'm gonna check my work, make sure I didn't do anything wrong. 4 pi a squared, yeah, that's good. Okay, last chance for questions on that one. Okay, this one should say question 10. Let's fix this, the flux from question 10. But this time, so we're just going to recompute and it should validate itself. It's completely different work, but we should get 4 pi a squared. It says to use the divergence theorem this time. Okay, any questions? So the divergence theorem is on the formula sheet. I'll show you. Up at the top. Here's the divergence theorem. So we're just doing this, this flux integral, but we're converting it to a triple integral of the divergence of the field. And now you're not on the surface. If you switch it to a triple integral, you're not on the surface anymore. You're integrating through the volume that's contained by the closed surface. Okay, so we're going to now move through the sphere. You can't say that x squared plus y squared plus z squared is a squared because you're inside the sphere and the distance to the origin will not be the radius of the sphere anymore. Okay. Does that make sense? So I'm going to go ahead and evaluate the divergence theorem, or just copy down the divergence theorem here. So I'm going to pop back here. So the divergence theorem says that if you've got this surface integral over a closed surface with an outward normal of f dotted with the surface, the vectored surface differential, that you can convert this to a triple integral of the divergence of the field and then just integrate dv. Divergence of a field is a scalar function, so there will be no more vectors remaining. I think I'll just do a quick picture of the sphere. So you've got a sphere like this. The radius is a, the surface is s, the inside is q. Okay, now we're going to do the horrible work of finding the divergence of the field. So that's going to be a little ugly. And I probably, just because of space, I'm going to probably just go real quick on this. So the divergence of the field, the formula is del dotted with the field. Okay, so this is, you know, del is the vector of partial derivative operators. Like this. And dotted with the field, of course, this is going to be x, y, z over the square root of x squared plus y squared plus z squared. And I'll just do this much for you. I'll say the partial with respect to x of the first component is, the first component is x over the square root of x squared plus y squared plus z squared. And you guys are all experts at integrals. This ends up being y squared plus z squared over x squared plus y squared plus z squared to the 3/2. So notice when we take the partial with respect to x of the one that has the x in the numerator, the result has a y and a z in the numerator. Okay. So I'm going to move that down a little and out of the way. And maybe put it in parentheses. So we can say, all right, so when you do this dot product, first the partial with respect to x, which I just showed, it's going to be y squared plus z squared over that denominator. Okay, now when you take the partial with respect to y of the component that has a y on top, you'll get something quite similar. The denominator will be the same, but the numerator has the x squared and the z squared, but no y. Okay, and then when you do the partial with respect to z, the numerator will have an x and a y. And again, this ends up being a scalar. So in the end, if you look, there's 2x squares, there's 2y squares, and there's 2z squares when you combine. So you end up with 2 of everything. So I'll write this as 2 times x squared plus y squared plus z squared, all to the power of 1 over x squared plus y squared plus z squared to the 3/2. So I think this just ends up being 2 over the square root of x squared plus y squared plus z squared. Like that. Okay. Now back to the integral. So I'm doing the divergence. So here it comes. The divergence of the field is going to be 2 over the square root of x squared plus y squared plus z squared. And that'll be dv. I'm still integrating over the entire sphere, through the sphere. We're not on the surface, we're inside. Okay, now, going into spherical coordinates, the integral is just 2 over rho. Because this denominator is rho. And of course, this dv is rho squared sine phi, d rho d phi d theta. Let me make some space there. Okay, so 2 over rho, and then we get a rho square sine phi d rho d phi d theta. Okay. Because it's just a sphere, rho has to go from the origin out to the radius of the sphere. phi has to go from the North Pole, where phi is 0, to the South Pole, where phi is pi, and theta all the way around the equator from 0 to 2 pi. Okay. And the nice thing is that these are all constant limits. And you can separate these into 3 integrals. You could do an integral from 0 to 2 pi on d theta times an integral. Oh, I should put a 2 out front because there's a 2 in there, isn't there? So let's put a 2 in front. And then if we do the phi, so phi, I just have a sine phi here. D phi, where phi, oops, where phi goes from the North Pole to the South Pole. And then rho, all that's left here is just a rho. So rho is going to go from 0 to a, and I just have a rho d rho. Okay. And then I'm just going to go ahead and most of this is really straightforward. So the 2 is there. The first integral comes out to be 2 pi. Okay. The next integral, you're going to get the antiderivative. You get a negative cosine phi from pi to 0. So you end up with a -1 minus 1. And there's a minus in front of it. So this ends up just being a 2, this next integral. Okay. And then the last one ends up just being a 1/2 a squared because the antiderivative of rho is 1/2 rho squared. So if you do that math, you'll get 4 pi a squared. Which is the same as the answer we got last time. So again, these questions will be like this on the exam, where you're going to do it 2 different ways. And if you get the same answer, you're going to feel like you must have done it right. Okay, any questions here? I think it's time for a break, right? So save up your question. I'll zoom out, save up your questions. We'll do a break till 7:41. And then you can hit me with your questions when we get back. Okay, so we're looking now at another surface integral, but this one's going to be the curl of f dot ds. There should be a dot right here because that's a dot product. And so they're asking us to evaluate the integral, the surface integral of the curl of a field. So I've gone ahead and drawn the surface. It says z is less than or equal to 1. So right here I have where z is 1. And of course that's z equals x squared plus y squared. And if z equals 1, then that's x squared plus y squared equals 1. Okay, so what I think I'll do is I'm going to project that down into the xy plane because we're going to need that as well. Actually, I'll just copy that and paste it down here into the plane and maybe do it in gray. Something like that. Okay, so it says evaluate the curl of f dot ds directly. Okay, so let's do the curl of f first. Okay, the formula is del cross f. And so you've seen this many times, or at least a bunch of times. So we do these partials, but the f is up here. The x component is y squared. Y component is x, and the z component is z squared. And we're taking partials with respect to x, y, and z. And I'll go ahead and put my I hat, J hat, K hat up there. Okay, so any questions about me computing the curl? Okay, so for the I hat component, we're gonna cross this way. Partial of z squared with respect to y is 0, partial of x with respect to z is 0. So the first component is just 0 minus 0, which is 0. Lovely. Okay, now the j component, I'll put the minus sign in front. And once again, we're going this way. Looks like it's all going to be 0 again. Partial of z squared with respect to x is 0. Partial of y squared with respect to z is 0. So again, this will be 0 minus 0. Okay. And then the k component, here we go. That's going to be partial of x with respect to x, that's 1. Partial time minus the partial of y squared with respect to y, that's 2y. So I think it's just going to be 1 minus 2y. Like that. So maybe just a little cleanup by calling it 0, 0, 1 minus 2y. Okay, any questions? Now, I need to figure out what ds is because I have to dot the curl with ds. ds is basically a vector whose magnitude is the surface area differential, but whose direction is normal to the surface. Surfaces have two normals, one direction and the opposite direction. This one wants an upward normal. So just for your notes, remember that if a surface is like z equals like a g of xy, then there's two formulas. One was for ds, the vector. So ds, the vector, for a surface integral, is negative gx, comma, negative gy, comma, positive 1 dA. That's an upward normal. You would reverse the sign for a downward normal. Okay, ds, the scalar, just to complete, we don't need this right here, but just to complete the notes, is the square root. You're just basically taking the magnitude of ds. So you're going to have a gx squared plus a gy squared plus 1 dA. So it's the magnitude. Okay, so here you can see here that this is our g of xy. Okay, so ds, the vector, I'm going to give myself a little more space for this. Using the formula I just gave, it's going to be negative gx, negative gy, oops, 1, and again, dA. Okay, any questions about that? Of course, this is going to be negative 2x, negative 2y, and 1 dA. Okay, any questions? So you have to kind of picture that the vector is kind of going up like this, normal, this way. it's pointing in. If you notice, the x component and y component are negative, so it's pointing in, but it has a positive z component, so that's a ds there. Okay, it's pointing in, but up. Questions? And maybe just since I've done ds over here, let's do curl f dot ds. So this is pretty straightforward. The curl is going to be 0, 0, 1 minus 2y, and then dot with a negative 2x, negative 2y, then a 1, and a dA. Okay, so we may as well just say, oh, oh, that's simple. That's just 1 minus 2y. dA. Okay. Any questions about all that? So now this looks actually super easy. We're going to switch to integrating over this region in the XY plane. So real quickly, I'm going to just make sure we understand that the region R that I'm integrating over is going to be this circle down here in the plane. So down here, the shadow that I've just cast, that's going to be R in the XY plane. Any questions there? Probably should have done it in gray because it's a shadow. Okay, any questions? Here goes. Double integral of curl f dot ds over the surface, which we're calling S. It's not a closed surface, so we don't put that ring around the integral signs. Hang on, I'm going to turn some light on. It's getting dark. That's better. Okay, so this is super simple, actually. This is just a double integral of 1 minus 2y dA. And dA is in the coordinate plane, so you're just integrating over R now. R is a circle, so it sort of makes sense to put this in polar. It's a circle of radius 1. So up here, z is 1, okay? So the circle is x squared plus y squared equals 1. Okay, just the intersection of z equals x squared plus y squared and z equals 1. Okay, so it's a circle of radius 1. We can put a little 1 down here as the radius of the circle, and here. And that's just the shadow of this surface down in the xy plane. Circle of radius 1. So we can go ahead and put it into polar now. So 1 minus 2y, this will be 1 minus 2, and y is our sine theta. But dA gets another r, dr d theta. Okay, r is going to go from 0 to 1, theta from 0 to 2 pi. Okay. I'm going to go pretty quickly through the rest of this and try and get into the space that I've got. Yeah, so that actually works out. What I've got here works out super nicely because when R is 0, it all vanishes. And when R is 1, then it's just super easy, right? So we end up with an integral from 0 to 2 pi. And you're just doing a half minus 2/3 sine theta, d theta. So that's nice. So here you can say that's going to be 1/2 theta. And of course, theta is going from 0 to 2 pi. And then plus 2/3 cos theta. And again, 0 to 2 pi. But cosine of 2 pi is the same as cosine 0. So this part, this second part's going to be 0. This part here. Okay, so in the end, you just get pi out of this. Okay, I'll just pause there and wait for questions. Any questions on 12? Okay, we only have 2 more, I think. So number 13 asks us to do number 12 again, but to use Stokes' theorem to convert it to a line integral, which is just crazy when you think about it. So let me remind you again. Stokes' theorem is on the first page. Where is it? Right here. It's the very last one. So we just computed the right-hand side here of Stokes, and you can convert it into a line integral, which looks easier. F dot dr. I love the idea of that. So Stokes' theorem's super nice. We're going to convert that. Okay. Any questions? Okay. So let's do it. Okay, so maybe just a reminder of the theorem. So we know that Stokes' theorem says that the surface integral of curl F dot with ds, the vector surface area differential, is equal to a line integral along a closed curve C of F dot dr. Love it. That's so much easier looking. Okay, so the field is pretty clear here. The curve C is actually the boundary of S. So let's put that down here. C is the boundary of S. Okay, so what you want to do is look at this. With an upward normal, you have to think about the right hand rule. So I'm going to try and draw a right hand again. I've done this before, and I'm going to do it just as badly today. Okay, these are my these are fingers. Okay, don't complain. There, fingers, love it. And then a thumb. Okay, so put a thumbnail on there. Beautiful. Right hand rule. So if the normal is upward, and I don't want to say upward because it could be downward. So here's the normal. No. Okay, here's the normal upward. Okay, and here's the orientation with the fingers. The curve's orientation. Am I right? break that. Kind of hard to read that. There, that's better. Okay, so that means my orientation, because I have an upward normal on this, that means the orientation has to go this way around the curve, which is nice because that's a counterclockwise orientation in the plane down below. Okay. Of course, this curve is not in the plane. Okay, so, but let's go ahead and put a C there to indicate that's our curve, the boundary of S. Okay, now we can parameterize C, and we'll need to do that. So let's go back down here. C is going to be an R of T. It's just a circle of radius 1. So the x coordinate is just cos t. The y coordinate is just sine t. And what's the z coordinate on that curve? Take a look at it. Anybody? You know up here z is 1, right? And it's z, and it's a constant height everywhere on that curve. So the z coordinate you need to make 1. So now any reference to x in the integral will be changed to cos t. Any reference to y will get changed to sine t, and any reference to z will be 1. Okay, again, now you live on the curve, so you can make certain assumptions about these variables. We better do dr, I guess, so let's do that real quick. So dr, going to have a negative sine t, a cos t, and a 0 dt. Okay, any questions? My field, I wonder if we should break down what the field is. So we can copy that down from up above. It's y squared x z squared. So let's do that down here on the right with the other stuff. So our field is y squared x z squared. Okay, now y is sine t. So this is going to be sine squared t. Then x is cos t. And then z squared, that's just going to be 1 square. Okay. Okay, because again, you're only evaluating this field at points along the curve, because on a line integral, you're restricted to the curve. Okay, is there any question here? So when we do this integral, the field becomes sine squared t, cos t, 1. And dr becomes negative sine t cos t 0. And then we'll put a dt. And then as before, we're going around a circle of radius 1, so it'll go from 0 to 2 pi on t. So any questions there? Okay, so let's do that dot product here. So we're going to get an integral from 0 to 2 pi. So you're going to get a negative sine cube t, yuck, plus cos square t, and that'll be dt. Okay, any questions there? Now, I'm going to have to split this into two integrals. I think that's kind of obvious. So I think obviously, I think it's kind of clear. I'm going to have to do one integral with a sine cubed t from 0 to 2 pi, negative sine cube dt. And then the other one looks easier relatively. So we get an integral from 0 to 2 pi, and we're going to have that cos square t dt. So with a sine cubed here, we're going to have to write that as sine times 1 minus cosine squared. So let's go this way. Integral on the first one with a minus sign out front, we're going to write sine t, and then a 1 minus cosine squared t dt. This is standard for powers of sine or cosine. Right here is sine squared t. That makes sine cubed. Okay, 0 to 2 pi. So on this one, u is cos t. And negative du. Oh, no, du is negative sine t dt. We happen to have a negative sine t. So that'll be nice. Plus the next integral, we'll have a 1/2 integral from 0 to 2 pi with, again, power reduction. So this will be 1 plus cos 2t dt. Okay, so next you end up with an integral of just 1 minus u squared du. Okay. What's interesting is that if you look at the limits, when t is 0, u is cosine of 0, which is 1. So the lower limit becomes a 1. And now on the upper limit, t is 2 pi, u will be cosine of 2 pi, which is also 1. So that first integral goes from 1 to 1, and so therefore that's just 0. Okay. The next part gets a 1/2, ends up with this just a t. So I'll put it in parentheses. There's a t from 0 to 2 pi. Okay. And then plus a 1/2 of sine 2t. Also from 0 to 2 pi, but those are both going to give a 0. So this whole thing here is 0. In the end, you just get a 1/2 times 2 pi, which is pi. Okay, and once again, you see this is the same answer as before. So just note, we're just recomputing these things with completely different methods and getting the same answer again after again. Again and again, I guess. Okay, is there any question about that line integral? I think there's only one problem left. I bet we can do it in the time allowed. Okay, I'll just wait for questions just for another sec. So you guys okay? So all these fancy integrals, it's nothing more than just doing substitutions. You just got to make the right substitutions. You know, what's X, what's Y, what's Z, what, you know, what's the substitution? There's always a substitution you have to do. So you end up just with a regular double or triple integral or single integral. Okay, one more. So this one says find the moment of inertia about the z-axis of a sphere of radius a whose density at any point is proportional to the distance to the center of the sphere. Okay, so that sounds pretty straightforward. So the distance from the point, any point, x, y, z, to the origin, the center is the origin for the sphere, is the square root of x squared plus y squared plus z squared. Which is just rho. So that means that the density function delta of x, y, z, that's mass density, it says the density is proportional to the distance to the center. So we can say that this is some multiple, some constant of proportionality times rho, the distance to the center of the sphere. This is, we don't put the radius of the sphere in here because this is not a surface integral. You're integrating through the solid where rho is always less than or equal to the radius of the sphere, but it's not, rho is rarely equal to the radius of the sphere. So you can't say rho is A when you're integrating inside the sphere. If you're just on the surface with a surface integral, then you can say rho is A because you're on a surface integral, you're forced to live on the surface, and everywhere on the surface rho would be A. Okay, is there any question about this? You can see I really like doing moments of inertia about the z-axis. There's just something about it that I like, so be ready for that. Okay, IZ is the moment of inertia about the z-axis. Okay, the formula is it's just a triple integral, if it's a three-dimensional solid, through the solid Q of, the formula is just x squared plus y squared. That's the distance squared to the z-axis. And remember, moments of inertia are just distance squared times mass. So here's the distance squared to the z-axis times the mass, which is mass density. That'll be delta of xyz times volume, dv. Okay, so that's the formula for the moment of inertia about the z-axis. You might remember that r squared, is x squared plus y squared. The delta of xyz is k times rho. So I've got some confusion with my coordinate systems here. Maybe I'll just remind myself for spherical coordinates. I don't need much of this, but real quick, x, this is spherical. X is rho sine phi cos theta. Okay, y is rho sine phi sine theta. Z is rho cos phi. And just in case you need it, R is rho sine phi. Okay, and you can remember, all the other stuff. dV is rho square sine phi. d rho d phi d theta. Okay, you should know this. I would hope you have this memorized. Okay, so this guy right here, I think we can go with this now. Let's go ahead and put it into spherical. So the r squared is going to become rho sine phi quantity squared. Yeah. The delta is just going to be k rho. And then, of course, dv gets to be rho square sine phi, d rho, d phi, d theta. You're on a sphere, so rho must go from the center to the outer edge of the sphere, to the edge of the sphere where rho is a. That takes up all values of rho inside the sphere. Phi must always go if you go from the North Pole to the South Pole, then that will be the range for phi. So 0 to pi. At the North Pole, phi is 0. At the South Pole, phi is pi. And theta goes all the way around the equator if you want the whole sphere. So 0 to 2 pi on theta. Okay. So this is horrible looking. I think I'll clean it up. Am I going to evaluate this? Yuck. What do you guys want to take a vote? It's only 8:16. We can do this. I'm gonna have to write smaller though. Okay, the nice thing is I got a sine cube phi. Ugh. Okay, here we go. So equals integral 0 to 2 pi, integral 0 to pi, integral 0 to a. Looks like I have a rho to the 5th. And then there's a sine cubed phi. Right, and then just d rho d phi d theta.
You have your constant too.
Thank you so much. You get a star for the day. Super exciting, Anna.
Very.
Okay, so then do remember sine cubed is going to be sine phi times 1 minus cos square phi. That's what you have to do to integrate a cubed on a sine or a cosine, basically. So here we're going to rewrite this with a k. And I'm going to bring the d theta separately. I think I'm going to break this into 3 different integrals. So we're going to have the d theta part, so 0 to 2 pi on d theta. You can only do this if all the limits are constants, times the integral from 0 to pi. Now I'm doing phi. And phi is going to be, so here I'm going to have a sine phi times 1 minus cos square phi d phi. And then rho, I just go 0 to a. And it's rho to the 5th d rho. Like that. So here, on this nasty integral on the inside here, I guess u is cos phi. And I think, of course, the derivative is going to have a negative. So let's say negative du is sine phi d phi. Like that. Okay, and so let's see what we get now. I think obviously there's this k. The integral on d theta from 0 to 2 pi is just the length of that interval, so that would just be 2 pi. the next part, we better put the minus sign in here somewhere. So I'm going to put the minus sign out front if you don't mind. Okay, so we're going to have this integral with, it'll be 1 minus u squared du. We'll have to figure out the limits. So when phi is 0, u is cos of phi, which is cos 0, that's going to be 1. So we'll put a 1 here as the lower limit. And when phi is pi, oh, did not mean to do that. When phi is pi, u is cos phi, which is -1. So again, whenever that differential comes out negative, you can expect the limits to get flipped. It just kind of reminds me of the Jacobian. When a Jacobian comes out negative, your region's been turned upside down. Somehow it gets reflected through itself. Okay. And I think we're okay there. I can switch those limits if I make the integral positive, which is great. It should be positive. This next part is a 1/6, and it looks like it's just going to be a to the 6th here. So here, let's see, what do we get here? There's a k, there's a 2 pi, there's a 1/6 a to the 6th, and then there's this integral from -1 to 1. I've made it positive, the minus sign's gone. And we just have 1 minus u square du. And I think I need more space. So this is going to be 2k pi. So 2k pi a to the 6th over 6. I guess I should reduce that. So let's say k pi a to the 6 over 3, right? And taking the antiderivative now, you're going to have u from -1 to 1 minus 1/3 u to the 3rd from -1 to 1. Kind of out of space, so I'm going to try and redeem some space for myself here. That's pretty good. Like that, I guess. So here I get k pi a to the 6th over 3. And what do you get there? You get 2 minus 2/3. So that's 4/3. Okay, so k pi a to the 6th over 3 times 4/3. So let's see if we all agree that it's 4k pi a to the 6th over 9. Okay. If you don't like it, I'm sorry. Ask for your money back. I don't know who you'll ask. Okay. Pretty good review, pretty solid. Any questions about this last problem?